All right, looks like it's about that time. Thank you all for joining us today. I'd just like to introduce Adam Spiegler from University of Colorado, Denver, presenting Exploring Differential Equations with Interactive Jupyter Notebooks. Thank you, Adam.
Yeah, well, thank you. Thanks for having me here. Yes, my name's Adam Spiegler, and I am at University of Colorado, Denver. And the plan today is to kind of just talk about some materials that I've been creating and using in my differential equations course, give a little demo of those materials, and just talk about some of the work and observations to those materials. Yeah, I want to also kind of talk about the background, because this fits into a larger project that we've been working on in our curriculum at University of Colorado in Denver. But yeah, mainly the goal is to just kind of give a little tour of Google Colab if you're not familiar with that, and show how we developed interactive materials for differential equations course, all using Colab. So kind of the genesis behind this in large part was this is results from a survey, an exit survey that our Math BS students take when they finish our program. And they're referring to this class called Math Clinic. And so Math Clinic is a poorly named class. It's like a senior capstone class where we have mentors from different companies in the Denver area that come in and have kind of really interesting projects for the undergrads to work on in groups. And in large part, almost all of those projects involve data and modeling and coding. And these are some of the comments that we were seeing from our students. Things along the lines of, we need a heavier focus on coding. Their only exposure to coding was in this last class that they were taking, and a desire to have coding integrated earlier. And this was also feedback from the instructors of the class, were also wondering, why aren't the students more prepared for the projects that we're working on in this course. So talking with some other faculty in the department, we wanted to not just create like a Python coding 101 class and then not have them use any coding in the curriculum until they get to this final class, because they probably would have forgotten that knowledge anyway. So we wanted to do this kind of more cohesively, building students along the way, and reinforcing this throughout our programming courses where it made sense. So our department put together a proposal for the Colorado Department of Higher Ed to create a bunch of these materials as open education resources, as OER. So it was an OER grant program, and we plan to kind of redesign and create course materials for a bunch of targeted classes that I've got listed here. So we kind of first created this intro to programming for data science and data wrangling class, and we were rolling out new data science programs in our department. And so we didn't want to have linear algebra for data science, which is what the administration was kind of expecting us to do. So we thought we wanted to integrate coding into these different classes and kind of build their way up. So the courses that are listed in black, these were courses that use Python. Some of the courses use R. And we had maybe about 4 faculty that were involved that were creating content for these different courses. And I worked on the differential equations, the stat theory, the linear algebra piece. So I'm kind of at the 3000 level piece that was trying to bridge the gap before these students were getting into the 4,400 level courses. So all of these materials are open. They're free to use for anybody. So if you're interested in checking these materials out for any of these other courses, we've got a GitHub repo group, and you can see all these different repos in there for the different classes. But I'm going to focus on the differential equations material. But kind of the motivation behind our project was, well, we wanted this to be free. So we wanted this to be like inclusive to all students, and we didn't want to price anybody out of majoring in math or data science. And we wanted to better prepare students for the careers that are hiring. So we just, they're all essentially wanting students that can analyze data, and oftentimes that involves writing code. And in addition, we wanted to just make our classroom environments more lively and more fun, and kind of build kind of this experiment mentality with mathematics, where a lot of other STEM fields, physics and chemistry and biology, they have labs where they can like play around with the concepts and run experiments and see the field kind of come to life. And we wanted to create a similar environment for math students to kind of play around with the concepts and actually see how they work in practice. And so we use Jupyter notebooks as this environment to create these virtual laboratories for them to play around. And so our kind of, or at least my goal with these materials, is to have students become like mathematical experimentalists. And as I walk through some of the materials, kind of the goals of using these materials are mainly just to make things more tangible and lively and fun. That's kind of always a goal in the course. But we want to use this as a way of helping students visualize concepts and discover patterns, testing conjectures, playing around with parameters in models, and just really kind of just bridging this gap between things that we kind of learn theoretically and how do we see these things in practice. And so the computing that we used Jupyter notebooks and Jupyter notebooks. These are free interactive computing notebooks that support a whole bunch of languages, but most commonly people use Python when they're working in Colab. And as we take a look at some of the materials, you can see that it's a nice environment to weave together text and code and applets, widgets, and videos and other things all into one document, so they don't have to, have 5 different files related to one lesson. And the way that they are opening and interacting and editing, saving these Jupyter notebooks is we use Google Collaboratory, which is a cloud-based version of Jupyter. So if you're kind of new to this terminology, you can think of like a Jupyter notebook kind of like a Word doc, and then Google Collaboratory is kind of like the equivalent of Google Docs. So it's just a cloud-based version to work with these files. And we've tried other, or at least I've tried other forms also free to interact with Jupyter notebooks, but it's just having the cloud is incredibly nice. Not having students to have to download and install Python on their computer is really nice, since things can go wrong sometimes if you're installing a new version of Python. So this kind of clears up some confusion maybe in the first week or so when students are trying to get their technology going. It's a really smooth process. Okay, so just to talk about the structure of the course at CU Denver before taking a look at the materials. So the students in my class, these are math, engineering, econ, physics students. So we get kind of a mixed bag of students, and I would say it's a pretty even mix of these different programs. And there's no programming experience needed in the class. So although we have this intro to programming class, I don't require students to take it. Most of them have not taken it actually. So we start very, very simple in the class. And as far as the makeup of the Math BS students, I don't know about some of the other majors, but for our majors, it's 40% are first generation students, 58% of them are transfer students. And so these are students, we're kind of a city campus. So these are students that typically spend 2 years at a community college, and then they start at CU Denver in their junior year. So for many of these students, they're taking their calculus at the community college, and then they're coming to CU Denver, and this very well may be their first math class that they're taking at CU Denver. And our classes meet twice a week, an hour and 15 minutes. And the way that I structured class is students, it's kind of like a flipped classroom where students would watch a video before they came to class. And then in class, we're doing active learning, working in groups, and they're running code and they're working with the notebooks that I'll show in a moment. And the technology that students need in order to access and interact with these notebooks is just some device that has a browser and a connection to the internet. So there's no additional software. These work on any computer, any tablet. They work on phones, smartphones. So it's pretty minimal technology requirements. And I also want to stress that the class is a differential equations class. So it is not a coding class. So I'm not really spending time getting into the fundamentals of coding or having them do anything too difficult, to be honest. It's a differential equations class, and we want to use coding really as a tool for just exploring differential equations and getting their toes kind of in the water of coding and trying to make the coding really accessible and fun for them so that they're encouraged to take some, to build off of those skills and take more classes that you would. Okay, so I am just gonna paste a link to this if that's easier for you. Here's a link to the textbook. And so, sorry, I just saw that there's a question about Colab versus CoCalc. I am not totally familiar with CoCalc, to be honest. But maybe if you have some time, I would be curious to hear about it from you. So sorry, I just saw your question, but I can't comment on CoCalc, but I've been using Colab a lot, and I really love it, but I'd be curious to kind of check out CoCalc as well. But if you have not seen Colab, I'm gonna exit out of this, hopefully, and be able to share my other screen where I've got this opened up. Here we are. Okay, can everyone see the new screen? Okay. Here is kind of a static version of this. So this is just an HTML document. So I have a bunch of Jupyter notebooks that are separate files that I kind of zip together using this Porto package, and it creates a nice static HTML file. And you can kind of see the outline of the topic in the class. So each of these notebooks has a link on top, so students can click on this link, and when they do that, they get taken to an interactive version of it. They get taken to Google Colab, and now they've got an interactive document. And that's what we're looking at here. And so if you've got this opened, feel free to do whatever you want to this document. This is like a shared file that only I have permission to edit it, so you can't kind of mess this up. But if you do want to make some changes and save it, there's a little button up here that says copy to drive, and then you can kind of create your own version in your own drive. So the only technology requirements I should append that students need if they want to save these documents is they need a Google account, and that is usually not an issue. Those are free, and a lot of students have those already, but they do need to have access to Google Drive. Okay, so this Colab notebook, they consist of two types of cells, what are called text cells. So that's what we're looking at here. And if you double click on any text cell, you can kind of see the raw text on the left, including any LaTeX that you want to use. And then you get the rendered text on the right. So students can kind of edit the text pretty similar to how they might edit any other Word document. And so this is kind of our first day in the class. I think it's the pretty standard stuff. How do we read differential equations? Start with some simpler models. What does it mean to be a solution, et cetera? But then I want to kind of talk about how we integrate coding into that first day, kind of motivate why we're using Python in the class. And then I introduce them to the SymPy package. And so these are the code cells in the notebook. And so at any point you're moving around in these notebooks, you can add code cells or text cells, and then you can just run them. I get a warning that this is on GitHub, and then you can kind of just run the cell. Right now, it's just setting up the connection at first. But on the first day, we just have students think about how we can define parameters and variables, how we can define functions, and then how we can differentiate functions. And it's fairly intuitive. So for any kind of instructors out there that don't know how to code in Python, I had no idea how to code in Python up to very recently. If the students can learn it, it's totally accessible for anyone teaching differential equations. There's kind of no expectation of any prior experience with this. So we have students kind of taking derivative, and then we have them doing some integration, which is also kind of fairly intuitive type of stuff. We just say integrate this thing, and then they're able to go ahead and try and solve their first differential equation using Python. I mean, this is really just an integration problem, but at least they're able to see how we can use Python to help us solve some differential equations. And so I like doing this on the first day, kind of telling students, here's how you could do calculus with Python. This really helps even the playing field in some sense for the students that come into the class that have weaker calculus procedural skills. The ones that have good skills, they typically start pretty well. The ones that come in after a longer break from calculus or with a weaker background, it's hard for them at first because they're practicing all of those skills, maybe relearning them, and they're trying to learn the differential equations content at the same time. So this gives those students a way of kind of keeping up with the material and checking their work. And I try not to use this as a means of them avoiding learning the calculus, but as a tool to help them kind of relearn the calculus skills that they're going to need. So that's kind of what they might see on the first day of the class. And the kind of next day, we would go through and talk about slope fields. I'm not going to give you a full differential equations lecture. I'm sure you're all very well versed in differential equations, but just to kind of see how things flow. I had a graduate student that worked with me, and he created some kind of built-in functions for us to help with the visualizations, because those are often the trickiest parts, like plotting a slope field or a phase plane. So we kind of start with making sure that students have some sort of intuition for what slope fields are doing and how they're useful. Don't want to sidestep that. But after we get acclimated with what slope fields are, I just want to point out that we have a bunch of applets that are in this module called ODE tools. And if anyone is curious about like seeing the nuts and bolts of how these things work, the code for these are in GitHub, but we kind of sweep it under the rug for the students in the class. So if they want to plot a slope field, they just import this package, and then we set it up similar to how things work like on a graphing calculator, where they input the viewing window, they input the function, and then they have a plotter. So this is how we do visualizations. It's pretty similar with face portraits and other visualizations that we use in the class. So some of the things we want students to do on their own, and then some of the things like the visualizations, we have nice ways for students to do that in a little more kind of user-friendly way. Yeah, and so as the semester goes on, I just want to kind of illustrate the flexibility of using these documents, and that they're super nice. So here's like a unit on mass spring problems and resonance, and you can embed images, you can embed videos of breaking the glass with your voice, the bridge claps, all of the greatest hits. So students can play around, watch these videos. But then we have a question where they're kind of playing around with a mass spring model, and we have a fixed mass and we have a fixed stiffness, and they're playing around with the friction, and they have some intuition about what should happen with the mass spring, and I don't want them to disregard what their intuition. So we kind of build that intuition, connect it to the mathematics, connect it to roots of a quadratic equation, and then we've got these nice little applets for them to play around with and see how these things are behaving. So we have a little mass spring, and you can hit the play button here and see the mass spring move around. So this is kind of the undamped mass spring. And then they can play around it and see what happens when have an overdamped versus an underdamped, or find where it's critically damped and go just above and just below that. So they can just play around with models and kind of see it in action and test the mathematics that they've done. And similar story with like when we systems of differential equations and nonlinear systems, in Pendulum, we have kind of nice functions built in for plotting phase pane solutions, and students have fun just kind of thinking about how hard would I need to push the pendulum in order for it to go around 2 times and stop it and things like this. So it's a mixture of kind of building in some of the classical skills, but using the coding as a tool to check their work, build some conjectures, and try and understand some of the results that they're seeing. Okay, and I will kind of exit out of that and just come back to the slides to wrap things up. And this was my backup in case I did not have an internet connection, which would be really bad if you're on a Zoom meeting. Yeah, and so if as far as like the homework that students are working on, here's kind of some samples of the homework. So the homeworks are just Colab notebooks that I put up online, and students copy these Colab notebooks, and some of the problems are kind of the standard things like find the equilibrium, and students are doing really nice work. I mean, they're writing up nice solutions, some of them using LaTeX, and it looks great, and I'm able to just put some feedback along the side in terms of comments. So we have this kind of nice Google feature of being able to annotate their work. Some students are using Colab, and I let them decide kind of how much or how little they might want to use Python to answer these. And even when they're using Python, they're still not interpreting the output correctly. So here's a student that found the eigenvalues and eigenvectors, but doesn't have any of the constants in their solution. And then there are some students that don't want to learn LaTeX, and they don't want to type stuff up, and they just want to do things the old-fashioned way. This is not quite totally old-fashioned because they're using a tablet here, but they can certainly write up their work on paper, take a picture, and paste it in here. And I have some students that are handing their work totally on paper. So kind of I try and let the students come around to that on their own, as far as how much LaTeX they want to learn and things like this. So I just want to share some feedback before my talk is over. So this is some of the feedback. So I've been using these materials in my differential equations class for like the last year and a half. Been using these interactive textbooks, and the students have responded really favorably. It's been really overwhelming, good response. It has added some additional work into the class for them. I think they have to work a little bit harder, but they see the payoff of that work. It's something that they can put on their resume that they've done some coding in Python. And I think they're a little more eager to put in that work. And then after this last semester, in our last bigger graduating class in spring of 23, we have this same survey where we asked them like what was the most useful class, and it was almost always very negative about Math Clinic. And I'm really excited that after kind of updating this curriculum, that students seem to be prepared for Math Clinic. and it seems to be a more valuable experience for them. And that's great because that's our closest experience to like what they're going to have to be doing when they finish up their undergraduate degree. Okay, so I think I'm just about out of time. So I just want to kind of thank some of the people that helped with this. So Jonathan Hershey, he was a grad student that helped code up a bunch of these little applets that we use. And this was funded by the Colorado Department of OER. And we have a nice little OER conference every year that our governor actually comes to. So that's really cool to have, you know, support of our government that has been funding all sorts of opportunities, not just in mathematics, but in tons of disciplines. Yeah, and so if you have any questions about the materials, or if you have any interest in using them or adopting them or revamping them, they're open source and they're totally out there. Just ask that you don't charge other people for them, but otherwise you can do with them as you please. And yeah, so I think there is a question from Christoph. Yeah.
Yeah, thank you very much. I think this sounds like a fantastic, wonderful project, and it inspired me to also look at using Jupyter notebooks, which I haven't done. I had one quick question. At the beginning, you listed the courses for which you have been developing materials. And if I saw it right, calculus courses were not in that list. And I wonder why not.
Yeah, so let me, yeah, so these were the classes, and I'll just say for political reasons, it was a little bit harder to get this done at the calculus level because we have lots of other majors that are feeding into it, and it's a bigger class. And we had classes that were already using it at the upper level, so it kind of made, and they were already essentially using Jupyter notebooks there, so they had the materials somewhat written, and we kind of worked our way down. But I will say that I am currently writing materials, labs for Calculus 1, Calculus 2 class. And so, yeah, I want to funnel this down to calculus as well. I don't see any reason why it could not work in a calculus class either. Yeah.
Thank you.
But yeah, that's why we didn't start with calculus. It was kind of where we already had stuff created and who was already bought into this and who was not quite sold on the idea yet. Yeah.
Mm-hmm. Thank you.
Yeah. Yes, Mario.
Hi, thank you for your talk. I'm a faculty at Fresno State, California, and this semester I've been experimenting with having students play around with MATLAB in some way to again, make the material a bit more interesting. And so to that end, I had a question about the assignments. I know you sort of mentioned giving students flexibility in terms of the kind of the assignment, but are there any actual Python assignments that students work on? And if so, how is that graded?
Yeah, so I will say Python is integrated a little differently into these different classes. So for example, I'm teaching linear algebra right now, and it happens to be online. And so in that class, they kind of have their assignments, and then they have Python labs where it's just working on Python stuff. In the differential equations class, it's different. They have their homework assignments. There are some questions that they have to use Python. So it's kind of integrated in there. And there are some questions where they can choose which way they want to do it. So it's just one regular assignment, or I don't know how regular it is, but it's just like one homework assignment. Some of the questions, probably they don't want to use Python. Some of the questions, they may want to use it, they may want to not use it. And some of the questions, they have to use Python. Yeah.
So how are those assignments that require Python graded? You go in and look at code or?
Yeah, so those are hand graded at the moment, and it takes some time. I do have some help grading, which is great. But kind of one thing that I would really like to do with this project is I know there are some ways of auto grading Jupyter notebooks. I don't know how to do that, but that's something I would like to learn or find someone that knows how to do that, because I think that would help streamline things quite a bit to have some sort of auto grading on the Python labs. Yeah. I don't know
Yeah,
if anyone is familiar with that.
I use MATLAB, and thankfully there's a MATLAB grader, and that does some sort of basic standard automatic grading stuff, and that's definitely made it's been a positive thing for me at least, and I'm hoping for students. But yeah, hopefully there's something equivalent for Jupyter notebooks.
Yeah, there is. I need to learn it. Yes. Yes. Let's see. I'm just catching up on the chat, so sorry if I missed some questions. There's one about how do students know if and when they arrive at correct results? Yeah, so I mean, for example, if they're trying to solve a differential equation, you know, they could always check their work by hand most of the time, but this way, you know, I'll have them use Python to begin their solution and make sure that it works, for example, those types of things, or creating a visualization to kind of reinforce that, hey, I found this equilibrium over here, and I can see that it's a saddle point over here. So that those sorts of checks. Oh, okay. Is there any other questions? Yeah, Mario.
Yeah, I have another one.
Sure.
How has this sort of programming component to the class impacted the mathematical content?
I don't think it has, but maybe it should. I think maybe is my answer. Like I kind of took things that already existed and started to tweak those. That's probably, rather than just throw all that stuff out, and kind of introduced this stuff in addition to kind of supplement that. And I started off making it easy because I thought that that's probably better than starting off with it being really challenging for the students. There would be more of a pushback. But yeah, now I'm thinking about ways of, you know, are there some things that I should stop doing because we can do them with Python? And probably the answer is yes. And so, yeah, I think that these things are probably going to evolve as time goes on. But I don't think it has really sacrificed any of the content in the class. I haven't really changed that. It really hasn't made it any more difficult to get through that. It hasn't really slowed things down. So it's just kind of worked really nice at the moment, like kind of reinforcing the way that I've been doing things. But yeah, I think that there's an opportunity to do things differently with this. Yeah.
Yeah, because the first thing that comes to mind, at least for me, when I started playing around with MATLAB, is the drawing slope fields sort of by hand, right? And I used to do previously, I would have them draw sort of fill it in quite substantially by hand, or come up with these no-climb tricks of being able to fill in quicker the slope field. But now that I sort of do this with MATLAB, I sort of think to myself, well, why am I forcing students to do all of this hard work by hand when computers do it better, faster, smarter? But there's still some, you know, as you've mentioned, there's still some mathematical content for them to learn, but maybe, you know, not have them do all of that by hand.
Yeah, I'm kind of at the same place of like trying to figure out what is the right spot. Yeah, because I still teach null clients, and I think there's some value to them. It helps kind of get some intuition for what's going on in slope fields. But yeah, you could just plot them and I find them, right? You don't necessarily need to spend a whole bunch of time solving them by hand. But yeah, being able to like say like what is useful about null clients, what information can we get from them? So yeah, there's kind of, yeah, probably there's some stuff that I could cut out of that, and probably as time goes on, that will probably evolve in along the ways that I think you're thinking. Yeah. Okay. If there aren't any other comments, thank you so much for your time and your feedback. And just if you have any comments or questions about the work, feel free to contact me.